So selected results in real harmonic analysis in the Dunkl setting. These will be joint works with Jean-Philippe Anker and Agnieszka Hejna. So best regards to Jean-Philippe and many thanks to Agnieszka because she helped me to prepare transparencies. Actually, all the pictures are due to her. Now, this is perhaps, I'm sorry that, whoops. This is the plan of my talk. I will start by some notation and motivation and stating some basic results from the Dunkl theory. Then I will go to generalized translations of radial functions and applications. Then I will pass to perhaps the main topic of my talk, which is generalized translations, which are generalized translations of non-radial functions. And if time permits, I will pass to the applications and some examples. So let us start by a kind of introduction. Our goal is to define and study objects associated with the Dangle operators, which are parallel to ones from the classical real harmonic and Fourier analysis. Let me start by two perhaps main important objects, which are convolution and related with convolution translation invariant operators, Fourier transform. Thanks to these objects, we are able to solve, for example, heat equation, so distribution of temperature in time, or define and study function spaces like spaces, Hardy spaces, Biesov spaces, triple desorting spaces, Lipschitz spaces, using either Littwood-Pelly theory, maximal functions, or singular integrals. And of course, there is related with function spaces potential theory, which can be thought as a theory connected with powers of the Laplace operator. Okay, so now I will go to the preliminaries very, very fast because many objects were already defined in the morning in this conference, and all my I will try to keep notation from the articles of Charles Dunkl and Margit Ressler, and the results can be found there. Okay, so I will pass very, very fast. So for non-zero alpha, sigma alpha denotes reflection with respect to the hyperplane orthogonal to alpha. R will be a root system, which is the finite set of vectors, which is preserved by the action of reflections with respect to alpha from the root system. The root system will be normalized. And by G, we shall denote reflection group, which is the group generated by all reflection from the root system. And K will be multiplicity function, which is invariant under the action of the group, and it will be always non-negative. Okay. Now these are examples of root systems. These are product root systems. And I must say that analysis for product root system is much easier than for other systems of roots. Colors indicate values of multiplicity function. Same color, same value. And these are examples of non-product root systems. All of them are connected with symmetries of conformal polygons in the plane. These are root systems in R2. Okay, now there is W denotes the associated measure with the root system and multiplicity function, and we have control on volumes of balls from below and above by this formula, which I now indicate. What is important and positive for us that the measure W is doubling, satisfies the doubling condition. So the volume of larger ball can be controlled by the volume of smaller ball. Further, oops, I have problems with this homogeneous dimension. So we define the number bulk n, which is so-called homogeneous dimension. It is the sum of Euclidean dimension plus sum of multiplicity function computed over all vectors from the root system. It is homogeneous dimension because the volume of dilated ball by parameter t equals the volume of original ball times t to the power n. Now, our hero means the Dangle operator. It is just a perturbation of directional derivative by some difference operator, which of course involves reflections. And let me state some properties. First definition, if Tj denotes a canonical basis, then by Tj we shall denote Dangle operators with respect along Ej, along the vectors from the basis. Now, important properties which will be used very much is that the Dangle operators commute. The Dangle operator applied to a polynomial is a polynomial of lower degree. We shall use this property in our research. And another property is skew symmetry, which allows us to integrate by parts. Now, what is bad is that we do not have Leibniz formula unless one either F or G is G invariant. Okay, now we may define the Dangle operator, so we take a basis, orthonormal basis, consider J Dangle operators defined with respect to this basis, we square them and sum up over all bases. And one of the property of this operator is that the operator does not depend on the choice of the basis. Okay, and now the Dunkl kernel, we already know, will be denoted by xy, and it is a unique solution of certain system of equations which involve the Dunkl operator. And we know that the Dunkl kernel generalized exponential function, and it has a unique extension to a holomorphic function on Cn times Cn. And now having this Dunkl kernel, we define Dunkl transform, which is generalization of the classical Fourier transform. So the Lebesgue measure is replaced by the measure W, and the exponential function is replaced by the Dunkl kernel. And very important for us, second tool is the fact that the Dunkl transform or Dunkl Fourier transform is an isometry on L2, and the inversion formula holds. The inversion formula has this same form as the Fourier, as the original one, except that we have no minus here. So it reminds all these formula remind the classical formulas from the classical Fourier analysis. Now we define generalized translation using the Dunkl transform. So we take the Dunkl transform of the function, we multiply by character. This is not character, but we may think that it is. Unfortunately, it is not. And then we take the inverse. What is perhaps bad for us that we do not know if the translations are bounded. Generalized translations are bounded on LP spaces. Maybe it is not bad news, because thanks to that we have something to do. We may write papers. And the positive part on green is that the translations are contractions on L. There's a result of Tangavelu and Xu, which says that if function f is radial L1, then its translation, generalized translation, L1 norm of the generalized translation is controlled by the L1 norm of the function. And to prove this theorem, the following third tool, very important third tool for us, was used, and thanks to this tool, we are able to continue and build some real harmonic analysis in the Dunkl setting. So this is formula of Margit-Ressler for translations, generalized translations of radial function. So if f is radial function, f tilde say this is radial part, then the translation by vector x of function f computed at the point negative y is the integral of f tilde composed with the function a. The function a is defined here, and this integral is against the probability measure mu x, and we do not know too much about this measure except that it is probability and it is supported in the convex hull of the orbit of point x. So point x is here. Here is the orbit of the point x. So these are these points. And we take the convex hull, and we know, thanks to the result of Margit, that this support of the measure is contained in this set. So this is our very, very important tool. Okay, now we come back to the Dunkl Laplace operator. This is an infinitesimal generator of a semigroup of contractions on L2, actually of contractions on LP spaces. And it has generalized convolution form. So the action of the semigroup is by convolution with respect with the kernel, Gaussian kernel, each sub P. So if we take now translation of this kernel, we obtain integral kernels of the semigroup, and we have exact formula for these integral kernels, or for the integral kernel, which involves the Dunkl kernel. Unfortunately, not too much. The behavior of that function is, I would say, rather magic. Okay, so now let us define very important objects for us. This will be the function dxy of xy, and it is the distance of the orbit of x to the orbit of y. So how do we compute? We have 2 points, x and y. We take orbit of the point x, which is that set, and it turns out that the distance of the point y to the orbit of x is achieved by this point x. Actually, both points, this and that, must be in the same Weyl chamber. Okay, so now we have also very important inequality that the distance of orbit is smaller than the function a for eta from the convex hull of the orbit of x. And thanks to that, and thanks to the Margit-Ressler formula for translation of radial function, we can easily deduce that the Hitch kernel, integral Hitch kernel, is estimated by this function. So here we have this distance. I will come back to this estimate later on. So now, motivation. Having the objects like the generalized convolution, or the Dunkl transform, the Dunkl Laplace operator, and the Hitch semigroup generated by this operator, we may ask if there are theorems which are parallel to classical ones. So, and let me start by the first result in this, maybe not first, but one of the first results in this direction. This is result of Tangavelu Xu. The result says that chi is a characteristic function, is the characteristic function of the unit ball, and if chi sub t are L1 dilations of this function, if we consider the following operator, we convolve a function f with the function k sub t and take supremum over all t bigger than 0, and this maximal function is of weak type 1,1 and bounded on spaces, or t between 1 and infinity. And in order to prove this result, Tangavellu and Xu used semi-group approach, which is very much in the spirit of the book of Eli Stein, Topics in Harmonic Analysis related to the Lie-to-Lie theory. But now we may ask the following question. Can we deduce this theorem from estimates for generalized translations of the function chi sub t, or from the estimates of the heat kernel? Actually, both estimates are very, very much related. So this is our perhaps first, oops, something happens that, okay. So now, second motivation. We may define Riesz transforms in the Dunkl setting. So these are just compositions of the negative square root of the Dangle operators composed with the Dunkl operators, or in other words, we may define the Riesz transform using the multiplier operator with the multiplier Cj over the length of Xi. And Tangavellu and Xu in one dimension and Amri and Sifi for general root system proved that the Riesz transform is a bounded operator on LP and of weak type 1-1. Now, second, this motivates us to ask the following question. Can we build theory of singular integral convolution type of generalized convolution type operators? Or looking at the Riesz transform, which is defined by multiplier, we may ask for conditions on a function m from Rn to C such that the Dunkl multiplier operator or Dunkl Fourier multiplier operator is bounded on LP or of weak type 1-1. So this is our second or maybe third already goal. Now, another problem which one can attack is to study delta K harmonic functions. So many results was done by Gallardo and Rezek, but we may try to ask the following problem. The problem is to investigate conjugate harmonic functions. So this system of functions n plus 1 functions which satisfies the generalized Cauchy-Riemann equations. So here the classical derivatives are replaced by, say, Dunkl derivatives, okay, Dunkl operators. And of course, we consider this in the half space. So we take the product of half line with Rn. So we have additional variable t, and t0 means differentiation with respect to t. And there is some, we need also some control on the vector of such functions. We may ask if we can build a theory of Hardy spaces in the spirit of Stein, Weiss, Pfefferman, Koifman, and Latter, did this in the classical situation. Okay. Now we may study Schrödinger operators. So we may ask for some problems connected with Schrödinger operators built in the Dunkl theory. And this will be the subject of Agnieszka Hejna's talk tonight. The next problem that we can ask about analysis of operators of higher order operators and their fractional powers. Okay, so motivation is perhaps already done. And now let me come back to the estimates we have already mentioned. Unfortunately, from these estimates, we cannot deduce that the maximal operator from the heat semigroup is of weak type 1-1 or bounded on LP. So we cannot deduce Tangavellu-Xu result. So in order to do this, we need some improvement. So this is joint work with Jean-Philippe and Agnieszka Hejna. And the improvement is to replace the factor to the negative n over 2 by volume of the ball. Then the estimate of the heat kernel remains, say, Gaussian bounds of function spaces of homogeneous type. And thanks to that, that we have volume of the ball instead of this factor, we may prove that the maximal function, easily prove that the maximal function from the heat semigroup is controlled by sums of hardy liquid maximal functions at the points sigma of x when sigma runs over whole group G. Since we know that on spaces of homogeneous type, hardy liquid maximal function, which is defined here, is oblique type 1,1 and strong type P, and the sum is finite, we may easily deduce the Tangavelux result from the estimates of the heat kernel. And now I want to sketch the proof of this improvement. So important properties which are consequences of Margit-Ressler formula, that if F and G are radial, we have inequality that is smaller than G, then the same happens for translations. And the second property is the following. We take a function F, which is radial, supported by ball center at the origin and radius r, then the support of translated function is contained in the orbit of the translated ball. So we take the x is the vector of translation, we take the ball at center x and radius r, and we take the orbit of this ball, and the support of translated function is there. Okay, now let us fix some notation. So for f defined on Rn by f sub t, we shall denote L1 dilation of this function, and by f sub t x minus xy, we shall denote the generalized translation of the function f sub t by the vector x computed at the point negative y. So this notation does not fit to the notation of the heat kernel, because in the heat kernel we have parabolic scaling, but let us forget about it. Okay, now I will try to sketch the proof of inequality which replaces t to the negative n over 2 by volume of balls. How do we do that? Because the proof is actually very, very simple. So consider function tilde, which looks like Poisson semigroup on the real line and is pretty large number. And consider radial function, which is defined by the formula p tilde of x. And we may normalize such that the integral of p with respect to the measure w is 1. So important property is that the physical derivative of the function tilde has faster decay, like Poisson kernel has. Thanks to that, and thanks to the properties of the function a, we easily compute or check that the gradient with respect to y is fixed, controlled by the same function. So this is the gradient of the function is controlled by the function. And now fix x and y, consider the ball centered at y and radius 1. And consider supremum over when y prime runs over ball B of this function. So this is continuous. So the supremum is achieved at some point y0 from the ball, and let this supremum will be denoted by k. Now we know that this is supremum, so of x y0 and minus p of x y prime positive. By the fundamental theorem of calculus, it can be expressed as an integral of derivative. Now we use this estimate for the gradient, and from this estimate we can easily deduce that difference is controlled by a, which was the maximum, times the distance from y0 to y prime. So now we are on a small ball centered at y0 and radius, which is equal exactly the inverse of that number. We know that the function of xy prime is bigger than k over 2. Now, we know that the integral is preserved by the Dunkl translation, by the generalized translation. So we know that the integral of the kernel P with respect to y prime is controlled by 1. If we integrate over a smaller ball, means that ball, we have bounds from below. K is the volume of the ball. So it means that K is controlled by 1 over the volume of that ball. If we just divide by the volume of the ball. So we know that P of xy is smaller than K. K is controlled by the inverse of the volume of the ball. Volumes of the ball are comparable if we change this radius to 1. So we are done. And now if the function Q is radial and is controlled by such a function, then we may easily deduce also pointwise estimates using the formula of Margit-Ressler. So the translation of the function Q is controlled by this integral. The blue part is controlled by that part, and the integral of the, this is perhaps purple part, is controlled by the volume of the ball inverse. So we can easily replace now the function that of this type by exponential function and obtain the estimates for the kernel we needed. Okay. So let us say something more about these estimates. The estimates with this type are very symmetric as far as the action of the group G. So we do not see any difference. But we may expect that the main mass, if x is fixed, the main mass of the function should be concentrated near the point x. In fact, this is true, and we may improve the estimates by adding a factor which has Euclidean distance. Okay. So when t goes to 0, from this we easily conclude that the mass should be concentrated. If x is fixed, the mass of the whole mass should be concentrated nearby x. Okay. Here is the proof, and maybe I will sketch the proof of that fact. It is not difficult part. Again, we use Margit-Ressler formula and some direct computations of the Dunkl Laplacian applied to the Higg kernel. But I will skip the proof for this moment, and maybe I will come back if time permits. Okay. So this is the proof, and let me also mention that this type of estimates were announced by Waldeck-Hebisch with a proof which uses Poincaré inequality. Here our proof uses only Margit-Ressler formula. Okay, so I have problems? No. Now, let me say something more. Having this type of estimates for the generalized translations of radial function, we may apply methods of analysis on spaces of homogeneous type, because our estimates are have volumes of the balls and distances. Actually, we have two distances: orbital distance and Euclidean distance. And one example of application is the following: that thanks to these estimates, we may build theory of Hardy spaces in the Dunkl setting and prove several equivalent characterizations. For example, characterization by boundary values of conjugate harmonic functions, like in the classical case. Characterizations by maximal functions from heat semigroup or Poisson semigroup or other maximal functions. Characterization by the Riesz transforms, already mentioned. We may also build Liquid-Pelly theory and characterize by square function. And thanks to this additional factor, which has Euclidean distance, we may prove also atomic decomposition into atoms of Neumann-Weiss form. So each function can be decomposed into infinite sum of atoms, or maybe linear combinations of atoms, infinite linear combination of atoms, and the atom is supported by a ball. The infinity norm is controlled by the volume of the ball inverse to the power -1, and all atoms must have integral 0. So this is going to work with Jean-Philippe and Agnieszka. Okay, now let me pass to generalized translation of non-radial functions. So this is our goal, to investigate such object. And now there is a bad information. It seems that we cannot apply the formula of Ressler to deal with this problem. But bad information becomes good information, because actually we can apply the formula of Margit-Ressler for translation of radial function. And I would like to show you how do we do that. So the first theorem in this direction is to study support property of generalized translation. So if we have L2 function, which is supported by the ball centered at 0 and radius r, then its classical translation, so this is Euclidean translation, the Euclidean translation of such a function is supported by the ball centered at x and radius r. Okay. So, natural question: what can be said about support of generalized translation? So there is a result of Amri, Anker, and Sifi that such support is contained in the annulus, where inner radius is the length of x minus r. So think that x is larger than the length of x is larger than r, and outer radius is the length of x plus r. On the other hand, already mentioned result of Margit-Ressler implied that if f is radial and f is supported by the ball centered at 0 and radius r, then the support of the translated function, generalized, of course, I think about generalized translation, is contained in the orbit of the translated ball. So this is the translated ball, and this is its orbit. So it can be written also by the use of the orbital distance. So now, our first result is that we may skip the assumption that f is radial. So now we have L2 function. Support of s is contained in the ball centered at 0 and radius r, and this theorem says that generalized translation of such a function is contained also in the orbit of the translated ball. So let me say consequences of this. About consequences. First of all, the set, which is blue, is essentially smaller than the volume of annulus, than the annulus. For example, if r is 1 and the measure is just the Lebesgue measure, then the volume of translated ball or orbit of translated ball is constant, while the volume of annulus can be pretty large when x is large. Okay, So now I would like to give you a sketch of the proof of this theorem. So let us consider functions of that type. So we are pretty large and consider functions of that type. These are radial functions supported by the unit pole. The important property is that if we apply Dangle operator to such a function, we just obtain x to the j, xj times a function of the same type. So if we do it twice, then we obtain xi times xj again and multiply by the function again of the same type. Thus, polynomial of degree which is smaller than 1 times against the function of the same type. So if we do it more times, then what we get? That the higher order Dunkl operator applied to such a function is x to the alpha, the multi-index alpha, times the function of our type, plus a finite sum functions of the form. We have polynomial. Polynomial is of lower degree, so degree of the polynomial is smaller than the length of alpha, is the function of this type. So from this, we easily deduce by induction that the function x to the power alpha times PL can be obtained as a finite sum of a function of that type. So this is Dunkl operator, higher order Dunkl operator applied to a function of our type, of this type. So now we use the fact that the Dunkl translation or generalized translation commute with Dunkl operators. So from this we know that since GL is radial, okay, translated function has support in the orbit of translated ball. Okay, so this function has proper support. If we apply the Dunkl derivative to such a function, support doesn't change. So maybe it changes, but it is still in the orbit of the translated ball. So we know that translations of these functions are supported by the orbit of the translated ball. Now we see that functions of that type form linear combination of function form algebra. So we may easily apply von Weierstrass theorem to prove that such functions are linear combinations of such functions are dense in L2. Now we use very easy density argument to prove this theorem. Okay, so now let me state very important lemma. We call this lemma key lemma because it allows us to play with translation of non-radial functions. So the key lemma is a consequence of the previous theorem, and it says the following. We take a radial function which is continuous supported by ball center 0 and radius R1, and we take any other function which is L1 function supported in the ball centered at 0 and radius R2. If we take the convolution of these two functions and translate them by vector x, this is of course generalized translations, so the L1 norm is controlled by L infinity norm of the function phi times L1 norm of the function L1 times expression which depends only on the radii. Now we see that on the right-hand side, we do not have x. So this estimate is independent of the vector of translation. Okay. Let me now give, so this is the proof, and I will of course skip the proof. It is again, not difficult proof. This is the whole proof is written here, and I will skip the proof, but I want to present you some consequence of this theorem. So the consequence is the following. If we take, for example, Schwarzkopf's function, we take translation of this function by vectors x, then the L1 norm is controlled by a constant c, which is independent of X. How do we prove this? So let me sketch the proof. So forget that, so assume that G has compact support. For Schwartz class function, the proof is almost same. And assume that it is supported by the ball center at 0 and radius R2. So now we write G in the form. So first we apply higher order differential, Dunkl differential operator to the function G and take the inverse. So convolution with Jm is the inverse to that operator because this is so-called Bessel potential. So what do we know about Bessel potential? That it is radial, continuous, and rapidly decaying at infinity. So now we take the Bessel potential and decompose this into sums of functions supported by multiplication of functions supported by annulus. So we obtain the decomposition of the Bessel potential in the form of sum of functions phi j, and we may easily control the following. So I have the problem with this, I'm sorry. And we may easily control the support of function phi j. Phi j, for example, are support in ball centered at 0 and radius j+1, or we may take dyadic composition, whatever. They infinity norm are rapidly decaying because we have here j to the power negative m. They are radial. The support of f is the same as the support of g, because this is just Dunkl differential operator applied to the function g. We have L2 convergence, so we may just write the function g as a sum of pj involved with f. This is L2 convergence, so we may apply our key lemma to estimate generalized translation of Schwartz class function or CC infinity function. The L1 norm are uniformly bounded independently of X. Actually, we may prove more that if we have Schwartz class function, we dilate them and compute its generalized translation, then we have the following pointwise estimate. Consequently, this estimate allows us to prove that the maximal function associated with convolution with non-radial kernel of weak type 1,1 and bounded on spaces. Okay. Now, let me say that in her PhD thesis, Agnieszka proved the result because she added also a factor which contains Euclidean distance. Now, this is for the function phi, which is non-radial, and actually it also allows us to define Hardy space by using non-radial functions. Okay. Now, another application, the third application is the multiplier theorem of Hermander type. So assume that M is non-necessary radial function, and assume that it's, say, local Sobolev norm uniformly bounded. So this is classical Hermander condition with smoothness which is slightly bigger than the homogeneous dimension. So the theorem says that multiplier operator of the form that we take the Dunkl transform, we multiply by multiplier m, which satisfies this condition, and we take inverse of the Dunkl transform. This operator is of weak type 1,1 and bounded on LP and also bounded on the Hardy space. So we price that let me emphasize that we need more than the homogeneous dimension. Usually, we expect that half of the dimension suffices, but we cannot prove half of the dimension suffices because we do not know that the Dunkl translations or generalized translations are bounded on L1. If they are bounded, then we know that half of the of M suffices. Okay. With multiplier operators, we can connect singular integral operators. We know that multiplier theorems are very close to the singular integral theory of singular integrals, but we may study singular integrals separately. So we may prove the following theorem. So assume that we have kernel which is continuous and have some smoothness. The kernel is defined away from the origin, and it satisfies very, very natural conditions. So we have the integral over annuli over any annulus are uniformly bounded. We have some homogeneity property that if we differentiate the function k, we get some kind of homogeneous, this kind of estimates. And we assume that the limit of the function k when epsilon goes to 0 is L. Usually, this integral are assumed to be 0. Then this condition and then that condition is just 0. Then the operator which is of the form of the singular integral operator with kernel k is of weak type 1,1 and bounded on LP. So now we do not assume
excuse us, it's already 47 minutes
I
of
have
your
already
talk.
over the time. Okay, so let me finish by this theorem. So thank you very, very much for your patience.
Thank you very much for this exciting presentation of recent results on Dunkl analysis. Are there questions from the conference room?
Yeah, one question would be about the translation of Schwarz functions. You have this result about the boundedness of translation of Schwarz functions by a constant which is independent of the space variable by which you translate.
Yes, you are talking like me. Oh. You are talking about this.
The translation of Schwarz functions. I do not know the number of the page, but you have some.
No, it is. I have already flashed this. Yes.
No. So this was just that one norm of translates of Schwarz functions remain bounded by a bounded.
Yes, but this. Yes, this follows from that also.
Yeah. But my question is rather, can you imagine of any consequences of this? So not this here, but this boundedness result, which was on a different page, that this might have any consequences? Or does it have interesting consequences? Yeah, here it is on top. Yeah.
Yes.
Yes. Do you know further maybe consequences related to boundedness of Dunkl translations, so that it would be some step towards further results?
Well, no. For the
probably
I
not,
know what
yeah?
what you are talking. What do you ask? But actually, this constant C depends on the Schwarz seminorm of the function G.
Yeah. Okay. Yes.
So this is for fixed G. So the constant C depends on G. Actually, depends on the certain Schwarz class seminorm of G. So we need for this result we need some decay and some smoothness.
Yeah.
Of properties. Okay, and same is for that.
Mm-hmm. So I have another questions about. I mean, this is all in the flat case. Yeah. So if you look, for example, if you look into Littlewood-Paley theory, you mentioned this red book by Stein, about
Yes.
Littlewood harmonic analysis related to Littlewood-Paley theory, and there's a lot about compact Lie groups, or also in the end, there is a chapter about Sturm-Liouville operators, so just in one variable, and doing some, say, analysis in this kind with Poisson semigroup and G function. And has anyone ever tried to extend this to higher rank, say Heckman-Opdam, compact Heckman-Opdam setting?
No, well, actually, maybe somebody did it, but we didn't try. We, of course, study Paley-Littlewood theory, and we obtain estimates from below and above of the square functions, different sorts of square functions, but still we did not do anything more in the analysis you are asking for.
Mm-hmm. Thank you.
Other questions from virtual participants? I can't see. I have a very quick question. From your talk, we can understand that there are no more open problems for radial functions, radial Dunkl operator, radial analysis. Do I exaggerate, or is it true?
No, you exaggerate. There are still open problems for radial. Of course they are. So
Okay,
still the hit kernel is pretty, this is translation of radial function. And it is still, the behavior is still perhaps, well, open problem. We had some results in this direction, but still. So I want to say that the analysis of translation of radial functions is not finished.
Okay.
We can prove several results in the direction of real harmonic analysis, but perhaps there are some other questions which needed better estimates.
There is a question from Tomek Lux.
So I also have a question about estimates of radial functions. So you are assuming that in the first result, technical lemma, you are assuming that the radial function is bounded. So what about the case when you have a singularity at 0? When the radial function is exploding at 0, and then you translate.
Well, actually, you are talking about, for instance. So let me say that the result of Tangavelu and Xu, this was the first result which I flashed. Mm-hmm. So we know that the translation of if radial function is, say, continuous and L1, then the formula of Margit-Ressler works, and now we can apply some kind of approximation. So any L1 function can be approximated by radial continuous functions. Okay, and we have control on the translation of these functions which approximate, because we know that the translation of radial function is one norm is controlled. So this is a result of Tangavelu and Xu.
Yes, but you need this L1 condition when the explosion.
Yes, I need this L1 condition or L2 condition. Yes, actually LP condition, because translation also is LP normal is also controlled.
Yes, but it may happen that it's not in L1 nor in LP, and then there's the question, what's the order? So if you translate such a function, it may have singularities at the whole orbit of X, and then do you have any information about those singularities? Or?
Well, no, we do not have at this moment. Yes, we do not have. Okay, I understand now your question. You want to ask about you ask about the following. So have a function, take a function f, which is radial as has some singularity at 0. What about singularity of the translated function? Yes?
Yes.
Yes, exactly. So we did not study that.
Okay, thank you.
So I cannot answer your question.
I can't see further questions, so let us thank the speaker again.